All right, what do we got? 7.3, number 11. Is that what we decided, the telephone pole problem? All right, you have climbed to the top of a 7.5 meter high telephone pole. Just as you reach the top, the pole breaks at the base. Are you better off letting go of the pole and falling straight down, like the duck we just saw in my crappy demo there, or sitting on top of the pole and falling down to the ground on a circular path? Find your velocity when you hit the ground in both cases. Your mass compared to the poles is negligible. We'll go over this in class for sure. As a hint, to deal with the pole tipping over, it's converting GPE to RKE. And then it says, what height should we use to find the GPE at the start? Think about the high jump lab we did. Okay? So let's do this. Let's deal with the easy thing first. Let's deal with you falling, right? So here's the telephone pole. Here's you. Hello. I'm mad at you guys. I think it's a great drawing. All right. So here we go. Let's see. What do we know? We know up here your height is 7.5 meters. What's your velocity at the top? 0. If you fall straight down when you get to the ground, your height will be 0 and your velocity will be question mark. So if I call this point A and I call this point B, then I know that the total energy at point A ought to equal the total energy at point B. At point A, all of my energy is GPE, so that means the gravitational potential energy at point A should equal, at point B, all of my energy is kinetic energy. So I am looking at mass times 9.8 times 7.5 equals 1/2 mass times v squared. M's cancel, and then solve it, right? And V ends up being 12.12, 12.2, something like that. We'll just call it 12 meters a second. There we go. All right, so that's if you fall, as in if you drop straight down. Good? Notice the mass there did not matter, right? Okay, now, what if the telephone pole tips over? All right, so here's you again. All right, but if the telephone pole tips over, oh, I guess it would, well, whatever, you get it. And then here's you. Oh no, very unhappy. Okay, so this time it says assume that your mass is negligible compared to the telephone pole. So this time I don't care about your mass, I care about the telephone pole's mass, right? Okay, so considering the telephone pole, the idea is the telephone pole is tipping over and it's losing gravitational potential energy, right? All right, so do you guys remember when we did the high jump lab, I talked about this a little bit at the beginning before the lab, and I said that technically when you calculate the GPE of an object, right now my height is not 0. Okay, even though I'm on the floor. Why not? Do you guys remember what we talked about? Good, you measure the center of mass of the object. Okay, and my center of mass is about at my belly button. If I tip over, then my center of mass could be closer to the floor, right? But it could never really, I guess it could be so, but all right, so the idea is a telephone pole is more or less uniform. So if the whole thing is 7.5 meters tall, then its center of mass is going to have a height of half of 7.5, so 3.75 meters, right? Does that make sense? And when it tips over, that center of mass goes down to 0. Follow? So when calculating GPE, we consider the center of mass of the object. Okay? So what's the velocity before the telephone pole tips over? 0. But I guess really, since we're talking about rotation, the velocity is always going to be 0. So what we really care about is the angular velocity, which here is also 0, right? Because it's not rotating yet, right? Follow? All right. Then the telephone pole tips over. Okay, and right before it hits the ground, we're doing on time. Oh my gosh. All right, so right before it hits the ground here, the height is now basically, for all intents and purposes, 0, but now there's some angular velocity, right? Follow or no? Okay, so this problem is tricky. It's the first time where we can't use our rolling trick because the telephone pole isn't rolling. Does that follow? So we actually got to do some rotational kinetic energy. All right, so let's call this point A. We'll call this point B. So here we go. The total energy at point A has got to equal the total energy at point B. So that means the gravitational potential energy at point A has got to equal the rotational kinetic energy at point B. Let me pause there for a minute to make sure everybody understands what's going on there. Questions? Dennis?
Why is there no red rotating again?
It's not moving, it's rotating. Do you know what I mean? Like it, I know, how do I want to say this? In order for the telephone pole to be moving, it would have to be like moving.
Yeah.
Do you know what I mean? It's not moving, it's rotating, like a door, right? Follow, you guys? It's a subtle distinction, but a really important one. All right, so is everybody good? Okay, so let's see what we can do. So, does it give us the mass of the pole? It doesn't, does it? All right, well, let's see what we can do. So let's see. So we're going to have M. I said we're going to have M times 9.8 times my height, which is 3.75, equals, well, again, it's not rolling, so I can't use any of those shortcuts from the video. So I think I got to go 1/2 I times omega squared, right? This is the only problem we've done so far where you actually have to use this equation. Everybody good? All right, so we got to figure out something about I. So take a look at your rotational inertia sheet. And see if you can figure out which one of the shapes a tipping over telephone pole would be. Yeah, I think it's that second one. A thin rod, what does it say? A thin rod of any cross section about the end, right? So the first one on the sheet is this. If the telephone pole was somehow just like spinning in space, right? But it's not pivoting about the middle, it's pivoting about the end, right? So it's that second one, right? Okay? And so it tells us that I is 1/3 the mass times the length squared, right? Isn't that what it says? And L is what? Is it 3.75 or 7.5? Look at the sheet. Look at how L is labeled on the sheet, you guys. It's the whole length of the thing, isn't it? You guys see that? So it's the full 3.75. Or, sorry, full 7.5. Cool? Does it say L or R? I changed them all to R, didn't I? Oh, no, it is L. Okay, good. All right, so are we good? Yeah. Say that again?
How would you know to use the thin rod instead of just like...
Oh, I gotcha, because you're thinking it's a cylinder the tall way. Because the solid cylinder, look where the axis is. So you're thinking it's like this, right? But the axis runs up through the middle, so that would only be if it was spinning this way. Okay?
Right.
Because it's pivoted around the end.
Okay.
Does that make sense? So it doesn't, I see what you're saying. So it turns out that it doesn't really matter. See how it says thin rod, but then it looks like a rectangle? It says of any cross-sectional area. What it's saying is it doesn't matter what it's shaped like as long as the length is much more than the width.
Okay.
Does that make sense? Everybody good? Okay. Okay, so we're almost done here. So I'm going to just substitute this into here, and let's see what we get. So I'm going to just bring this thing down. So we got m times 9.8 times 3.75 equals 1/2 of this mess, 1/3 m times, our L is 7.5 squared times omega squared, right? Everybody good or no?
Then you can cancel out the M's and solve for W.
That's right. Cancel out the m's and solve for your W omega thing. I can't do that in my head. Who's got a calculator? I do.
I got 1.98.
1.2 what?
1.98.
1.98. Can anybody confirm or deny that number?
Yeah.
Yeah? All right, I'll go with it. So omega is 1.98. What are the units going to be because it's omega? Radians per second. All right, so which is faster, 1.98 radians a second or 12 meters a second?
1.98.
I don't know, apples and oranges. Can't compare radians per second to meters per second. What do I need to do? Use your jumper equation. You're at the end. You're traveling in a circle with a radius of 7.5. So V is omega r, 1.98 radians per second times 7.5 meters gives you just shy of 15 meters a second. So which one's better? Falling. Okay. And you guys saw that when I tipped it over, you guys all said that it looked like the meter stick was hitting harder, right? So that's weird. It takes more time to fall, but when it gets there, it's moving faster. Okay. Questions on that, you guys? All right. When do we get out? You think I would know this? 29? 30? 49?